Hey, we are going to do a lesson on set theory. There are three things that you need to go print from, let me get these dots off of there, that you need to go print from my math lab under document sharing. You need to print a preview for set theory, you need to print the notes for set theory, and you need to print the practice. We are not doing set theory inside of my math lab. This is our lesson for set theory. So get your preview out, be ready to answer on it. Ideally, you should answer it first using the set theory notes and then go answer the practice. But if you want to, put the preview and the practice out and work through them as we go through the set theory notes. We've taken about 6 or 8 pages of notes, and my coworker, Professor Orr, has condensed them down to just these 2 pages. So it's all condensed together. I will use different colors to pull pieces and parts apart, but I'm going to start with the outcomes. In our course, we're supposed to apply the language and the notation of sets. So I want us to start with the 3 ways that we can designate a set. One way is called word, the other is a roster, and the other is set builder. Make sure you're familiar with these 3 ways to designate a set. So starting with roster method. Roster means you're going to do a list of something, like a roster. If you play any sports, there was a roster of who's going to be playing for that game. But to do the roster, we can use words to describe and then turn it into a roster. So set C is the set of United States coin with the value of less than $1. So in words, we want all of the coins that have value of less than $1. Well, to do a set, we're going to use a capital letter and an equals and squiggly lines, braces. So just practice making them the best that you can. And if it's less than $1, you'll note that we have listed a penny, a nickel, a dime, a quarter, and a $half. And what you have are examples of a set in words, and then the roster method, putting the words into a list instead of just words. I know it's using words to talk about the words. We'll do an example at the bottom. So another is set builder notation. It's a set, and it's going to build sets. Let's look at the words. The words are, we need the set W, that's the set of all elements X, such that X is a day of the week. Well, one thing you need to practice is how to say the set builder notation. The set W is, and when you see the squiggly lines, and I've already said that part here, the set W, that's the first part, is, when you see the squiggly lines, we're going to say these words, the set of all, or the set of all elements. And sometimes we just get lazy and say the set of all. But we'll say W, or the set of W, the set W is the set of all elements, and then you say what the letter is, X. And then when you see that vertical line, you say such that. So when we see this vertical line, we're going to say such that. And then you say what's left. X is a day of the week. So I would practice saying that out loud. The set W equals the set of all X such that X is a day of the week. And that's it. And that's called set builder notation. And the words, well, we've been using the words to say that. If you wanted to turn that into a roster method, you'd say it was the set W, and what are the days of the week? So you would write out Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So you have all 3 examples right there. Here is an example of the 3 ways to designate a set. You can say it with words. B, it's the set of members of the Beatles in 1963. So we just used words to talk about a set. A roster, we're going to list them. So B, we're still using the B, is what's in that set. The members of the Beatles in 1963 would have been George Harrison, John Lennon, Paul McCartney, and Ringo Starr. And then finally, we're going to talk about our set using set builder notation. Here's where you get to practice. The set B is the set of all X such that X was a member of the Beatles in 1963. So before we go on to the bottom half of the first page, you might be completing your preview, you might be completing your practice, but you also need to consider creating flashcards of these concepts. It could be that these 2 pages are deceptive, but they are packed full of concepts, ideas, and thoughts that you'll need to know for our next test. Here comes, here are, this is. Here's another concept called the empty set. The empty set has another name called null set, and here's how it's defined. It's a set that contains no elements. You may say that the empty set can be written like this. There's nothing in it. It's an empty set. You may have seen people use the 0 with a line through it. That also means empty set. But one thing it is not is if you draw the braces and then put an empty set inside of it, it's no longer an empty set because the set actually contains the symbol empty set. So this is not considered empty set. We're moving on to another concept. When talking about sets, you can look at these symbols, and whatever those symbols are, we're going to discuss, define, look at an example, and that's something that you might want to consider putting on flashcards. So this symbol is used to indicate that something like an object is an element of a set. It helps me to remember that the symbol kind of looks like an E. So E, element, it's an element of the set. And so when you draw a line through it, the symbol, as you see there, it's used to indicate not an element. So we have 2 symbols to look at, either element of the set or not an element of the set. And so now we have a couple of examples. Determine if the statement is true or false. And to do set theory, I do a lot of scribbling, drawing, thinking off on the side, so that when it says R is an element of, okay, R is an element of. So I could even be asking myself a question, is R an element of? And you notice the A, B, C, D, and then the 3 dots. The 3 dots means it goes on and on and on and on until it has a place to stop, if it stops. And so this list is A, B, C, D, going on through the alphabet to Z. So would R be an element of this set? True. R is in there. The next question, is 7 not an element of here? Okay, here goes the true, false thinking. 7 is an element. No, it's not. 7 is not an element of this set. So is it true or false that 7's not an element? Well, it's true. 7 is not an element of that set. We're going to keep going with some more concepts. It's a great thing that you're listening to a recording, and you can pause this and think and move on, move back, fast forward, whatever you need to do. But just make sure these concepts are really solidified in your brain. So the set of natural numbers. So I need you to know a phrase called natural numbers. What are natural numbers? I like to say that natural numbers are what we do naturally. When you're little or born, you say the ABCs and your 1, 2, 3s. You do it naturally. There are counting numbers. So the natural numbers are either counting numbers, what you do naturally, and then it says here, it explains the 3 dots. It means there's not a final element. This one goes on forever. The one that we had right up here, it actually had some dots to say, hey, it's going to go on. It just means something's missing. That one actually ended. This one goes on forever. Represent the following sets of natural numbers. So we have a few more examples to look at. The set A. The set A is the set of natural numbers that are less than 5. Less than, so I can't equal 5. So 4, 3, 2, and 1. So the set of natural numbers that are less than 5. Got it. We're supposed to call it A. And so the set of numbers, natural numbers that are less than 5, that would be 1, 2, 3, 4. Let's do another. Part B. Or part B is the set B, and it's the set of natural numbers. The set of natural numbers, and what are the criteria? The set of natural numbers that are greater than or equal to 25. Greater than or equal to 25. So this time I get to include 25. I'll show a couple of them, but then I'm going to be like, I'm I'm lazying out on these dot, dot, dots. So that's the set of natural numbers greater than or equal to 25. I'll even do an aside here and go back to when we were talking about set builder notation. Set builder notation would look like this for part B. B is the set of all x such that x is greater than or equal to 25. Oops, and we'd also have to say, let me get rid of that right there. That's going to be, we would also have to say that x is an element of the natural numbers, because something greater than 25 could be 25.1. And we don't want 25.1. We don't want the decimals and fractions. We want it to just be the natural numbers. Part C is in set notation, set builder notation. And so we want C, and C is the set of all x such that x is an element of the natural numbers and x is even. It's a counting number. It's got to be even, and it's got to be a natural number. So that means I would start with 2. 4, 6, doesn't tell me I'm ending. So now I've illustrated the whatever it's asking for on C. I've illustrated it with a roster method. We're now on the back side of your set theory notes. We have a lot crammed in here, so make sure you're using highlighter or something to distinguish between the parts. So the definition of a thing called a subset. The definition is the set A is a subset of another set if all of the elements of the original set are also elements of this other set, like set B. So if set A is 1, 2, 3, and set B is 0, 1, 2, 3, 4, is A a subset of B? Well, it says A is a subset of B if all of the elements of A are also elements of B. Is 1 in B? Yes. 2? Yes. 3? Yes. So if all of the elements of A are in B, then A is a subset of B. But there's more. We also have another item called a proper subset. Proper subset. So a proper subset of a set. Set A is a proper subset of set B, and the symbol looks like this. If A is a subset and A and B are not equal. So up here, if this would have been what B looked like, then I could still say A is a subset of B because all of the elements in A are in the elements of B. But I couldn't say it's a proper subset because a proper subset is a definition, is that it's expressed as you see there, if A is a subset of B and A and B are not equal. Well, with my scribbles on the first part, this would not be a proper subset. But if I undo that, I could now say that in addition to A being a subset of B, A is also a proper subset of B because everything in A is in B, but they're not equal. Some more details. An empty set is a subset of every set. That's good to know. Furthermore, the empty set is a proper set of every subset except of itself. Equivalent sets. The definition of equivalent sets. Set A is equivalent to set B. That should be capital. It means that set A and set B contain the same number of elements. And we denote it as n of the A is n of the B, and in this case 5. And so if you look here, the set of A is the set of all x such that x is a vowel. And so we would say A is A, E, I over U, and it has 5 elements. Below it we have B. The set B is the set of all x such that x is an element of the natural numbers and it's between 2 and 8, not including. So that would be 2, 3, 4, 5, not 2. It would be 3, 4, 5, 6, and 7, and it also has 5 elements. So are these equivalent? Yes, because the number of elements in A and the number of elements in B are both 5. One last thing in this set of our page. We need to define what a universal set is, and it's defined as U. And it's all of the elements or members of any group under consideration. So, for example, we can define a universal set as the set of natural numbers, then that would be our universal set, and then we would play around from there. We could define a universal set as the letters of the alphabet, and we could play around from there. The thing to remember, universal set is going to be all. The last half of our second page contains the following. A complement. Definition of the complement of a set. If the set is A, its complement is A apostrophe looking like thing, and we call it a complement. An A complement is the set of all of the elements in the universal set that are not in A. So if A is the set of A, then A complement is everything not in A. For example, if we define U, the universal set, as a vowel, and then we define A as O and U. Remember, the universal set has already been defined as a vowel, A, E, I, O, and U. A is O and U, or includes O and U. Then what would be the complement of A? Well, the complement of A is everything in the universal set, everything over here in the universal set, but not in A. Well, O and U are in A. It's got to be in the universal set, so it's everything left over. So A complement would be A, E, and I. The last thing that we're looking at is called a Venn diagram. In our Venn diagram pictured, realize that the big rectangle represents the universe. And not all of the universe may make it into a circle. Harry did not. Notice that some people are Facebook users, some people are Twitter users. We have an overlap there. Bob is using both, but Harry is using neither. So it asks us to look around and do a few things. And I just said in words what we're supposed to look at. So who all would be included in the circle for Facebook users? Well, Al, Courtney, Frida, and Bob. And that's what they wrote out here. Who would be included in the Twitter users? Dave, Ernie, Gary, and Bob. That's what they wrote out here. But for the universe, we got to go include everyone. So Al gets included, and it looks like we're going by the alphabet here. Al, Bob, Courtney, Dave, Ernie, Frida, Gary, and Harry. And so let's play around and throw out one more idea. So what's the complement of F? And remember, complement means it's everything that's in the universe that's not in F. It's got to be in the universe, but not in F. Well, I'm going to just scribble out everybody that's in F. Well, that's an F. The F prime, the complement, is going to be everything else. So Dave, Ernie, Gary, and Harry would be in the complement. We have now finished our lesson on set theory. You need to complete your practice and complete your preview. You need to scan those and upload them per the directions that I sent in your weekly assignments.